Today, we'll discuss fundamentals and important information for using the tailstock on your CNC turning center. The tailstock option, available on all Haas lathes, adds versatility to the turning operations you can perform. But what do you need a tailstock for? Slender, flexible parts are probably the most common application where tailstock support is required. So what defines a slender, flexible part? The most common way is to refer to its length to diameter ratio, or L to D as it's often referred to. But let's be more specific. It really isn't enough just to look at the L to D ratio of the part by itself. When we grip the part, the effective L to D ratio changes. Here we have a 6-inch long by 1-inch diameter shaft. Its length to diameter ratio is 6:1. Now we clamp this shaft 1 inch deep with 5 inches extending outside the chuck. The unsupported region of the shaft has an L to D of 5:1. This unsupported region is what we need to consider. With this much of the workpiece hanging out, there will likely be problems cutting unless tailstock support is added. However, the same 6:1 part, clamped with only 3 inches hanging out, will probably not need tailstock support, because now the unsupported region is only at a 3:1 ratio. Once you've exceeded an L to D ratio of 10:1, parts become so flexible that even tailstock support may not be enough. So, to summarize, we recommend when unsupported L to D equals 3:1 or less, tailstock support is probably not needed. When a part's unsupported L to D ratio is above 3:1, now it's time to start considering tailstock support. And when unsupported L to D is over 10:1, we'll definitely need tailstock support and maybe something more, like a steady rest. This profiled and threaded shaft has an unsupported L to D that's beyond what is typically possible without a tailstock. Let's look at how you'd set up your tailstock for this part. Here's the material we'll be starting with. We already completed Op 1, where we turned the bar stock down so we can grip it with our soft jaws. Because our finished diameter will eventually get small at the tailstock end, we don't really have room for a large center drilled hole. So we'll choose this small number 3 center drill. The small center hole will also keep the live center's main diameter farther away from the end of the workpiece, since the live center doesn't sink as deep into the part. This provides additional clearance for the cutting path of the insert. But before center drilling, we need to prepare the end of the workpiece by facing it off. In this case, we grip the part in an extended position in order to face and center drill the part in the same place where the turning operations will occur. If you're concerned about facing and drilling an extremely long part like this, you should choke up so only a few inches are hanging out, and face and drill close to the chuck. You might be thinking, I've got this part sticking out pretty far. Isn't it going to deflect during the cut? Good question. Let's face and center drill our part and see if it does deflect. For safety, the facing and drilling should be run at slower spindle speeds, with a slow feed rate and a shallow depth of cut, so the shaft won't whip or bend. An extended part should never be faced and drilled at high RPM or cutting loads. The part can be thrown and cause damage, injury, or worse. Exercise caution and common sense when deciding what's safe for your setup. With the facing and drilling complete, let's check our part. Both the face we just turned and the center drilled hole have very low runout. Great! Okay, so we just saw the part get faced off and center drilled. These operations start off our program. Next, the tailstock moves automatically into position. With the part supported, the cutting continues. Using the Haas programmable tailstock motion is initiated from within a program. No manual activation is needed. Before we move on, let's stop for a minute and talk about center drill depth. We'll look at the important part of the center drill, its 60-degree cutting edge. The highlighted area shows us the full drill depth, but generally, you want to cut into your part up to about 90% of this full drill depth. Don't make the mistake of drilling so deep that you drill into the major drill diameter. Now, instead of a nice wide 60-degree flank, you'll be left with an edge at the face of the part, which will only offer a fraction of the engagement of a properly drilled center hole. Part stability will suffer. And though it may seem like an obvious point, it's worth noting that a surprising number of people will mistakenly use a 90-degree chamfering drill to make their center holes. This is what the contact looks like when a 90-degree chamfering drill is used. With only the bottom edge of the hole touching the center's tip, resistance to cutting loads will obviously be reduced. Always use a 60-degree center drill so the angle of the drilled hole will perfectly match the angle of the live center. Now that our part has a center hole, let's move on to how we command our tailstock and control where it moves. So, how would you tell the tailstock to move forward and retract? M21 is the tailstock advance command, and M22 is the tailstock retract command. Let's add these commands to our program. We cursor down to right after the first tool is called, and this is where we insert the M21 command. And at the program's end, this is where we'll insert the M22 retract command after axis motion is complete. Still another way to initiate a tailstock move is to use the foot pedal. Whether it's commanded from a program or by the foot pedal, when the tailstock moves forward from home position, it moves to what we call the retracted setting 105 position. From here, it will move back and forth between the 105 retracted position and the 107 hold position as you clamp and unclamp your parts. We'll talk more about these settings in a minute. When the foot pedal is used to put the tailstock in motion, either forward or in reverse, when you press the pedal a second time, the tailstock will stop as a safety precaution. Once it's stopped, pressing the pedal again will return it to the retracted position. However, it's important to note, when an M21 or M22 command has been issued, pressing the foot pedal will not halt tailstock motion. And there are several other ways to move the tailstock. You can use the tailstock jog keys, handle jog the B-axis, or command a B-axis move. But none of these should ever be used to clamp the part. To clamp your part during machining, use only the M21 command, or the foot pedal to initiate the M21 move. This is the only acceptable way to clamp your part. Using the handle jog keys, the rotary control, or commanding a B-axis move will not maintain full clamping pressure during cutting. With our M21 and M22 commands in place, let's look at where we're telling the tailstock to go. We'll start with setting 107. This defines where the tailstock should be when it's clamping the part. To find a new setting 107 position, we jog B-axis forward until it touches the end of the part. The B-axis position is negative 23.3. We add negative 0.5 inches to the negative 23.3 value, and we enter this new value of negative 23.8 into the setting 107 hold point field. This way, the tailstock tries to clamp at a point beyond where it actually touches the part, allowing for minor variations in part length. Let's test our new 107 value. The tailstock is trying to reach negative 23.8, but of course it stops when it hits the workpiece at negative 23.3. Great, the part is clamped. How about setting 106? This setting tells the tailstock when to slow down from rapid motion. We'll leave it set at its present setting of 2, which slows motion 2 inches before the hold point. With 107 and 106 out of the way, let's look at setting 105, which sets the retract point. Setting 105 defines how far away the tailstock retracts from the setting 107 value. Right now, setting 105 is set at 11 inches, and our tailstock is wasting a lot of time moving too far away. So we'll pick a new value of 3.5 inches. This keeps it closer when retracted, but it still gives us enough room to remove the part. Next, we've got setting 121. This is also important. When you use the foot pedal, setting 121 warns you when the tailstock is not clamping the part. Pretty handy. With setting 121 set to off, the tailstock moves to the 107 position, but it doesn't check if it's reached the part. So if your part isn't in the right place, the tailstock may not actually be clamping the part. That's why we recommend setting 121 should always be set to on. That way, anytime the tailstock is activated, whether by a program or with the foot pedal, it will fault out if it doesn't find a part. Next, we've got settings 93 and 94. These define a region around the tailstock, which acts like an invisible shield. This shielded zone moves with the tailstock. Setting 93 is easy to visualize. It's the distance from X0 down to the edge of the restricted zone. So to set this value, find the most extended tool on your turret and use that to check your clearance. So we jog the X-axis down towards the tailstock until we found the clearance we're happy with. Looking at the X-axis position on the screen, the reading is X, -7.63. So we'll change setting 93 to a slightly smaller value, like -7.6. Simple. Now, when X-axis motion moves toward the tailstock, it will halt just shy of -7.6 before the tool can crash. Okay, setting 94 is a little trickier. Let's move the tailstock back so we can look at how it works. Say, for example, we need to drill the end of this part mid-cycle. We don't want the turret to hit the tailstock as we retract at the end of the drill cycle. Setting 94 represents the difference between the position of the tailstock and the turret along the Z-axis, and it protects the tailstock from unintended Z-axis moves. Let's just say, for example, we just changed to a different live center, and now we want to increase our setting 94 clearance value. This is how we would do it. You jog the Z-axis towards the tailstock until you reach what looks like enough clearance. Then we look at the machine position value and subtract the B-axis from the Z-axis. In our case, we subtract -5.0, the position of the tailstock, from -8.82, the position of the Z-axis. This gives us -3.82. So let's round that up to a slightly larger value, just to be safe, for setting 94, to halt the tailstock motion whenever it reaches this new distance. When you take a closer look at this graphic, you might say, well, that red distance is obviously not 4 inches. Remember, setting 94 is actually the difference between the Z-axis and the B-axis machine positions. So we know how to control the tailstock's position and protect it from crashing. We're ready to clamp our part. But one question remains: how much tailstock pressure should we use? Many machinists believe it's best to use as much tailstock pressure as possible so the part doesn't come out. Others believe you should hold your part with as little pressure as possible so you don't deform your part. You might be thinking, well, why shouldn't I just use max tailstock pressure all the time? Well, one important reason is, as tailstock pressure increases, deflection in the workpiece and in the machine also increases. Sometimes this can affect accuracy and repeatability. You can also increase wear on your live center, and now you're adding more force to the already existing axial cutting forces, which are trying to push the part inward past your jaws or collet. To explore this question, we're going to perform a few more of our famous real-world tests to demonstrate why we here at Haas recommend starting with a tailstock pressure of 200 psi when setting up a new part. First, it's helpful to figure out how much force is actually being applied when we set the tailstock to 400 psi. Using this load cell, we can see that our max tailstock pressure at 400 psi translates to a little over 1,200 pounds of force, the same as what the chart on the side of the machine says. Let's start with a static test to see if part deflection is affected by tailstock pressure. We've got this 1-inch diameter shaft held 10 inches out from the chuck, with the tailstock clamping it at 200 psi. To simulate a cutting force, We'll use the x-axis to push with the turret against the load cell, which in turn will push against the shaft. And finally, we'll use an indicator to measure how much the shaft deflects as the load increases. Okay, so we're jogging x-axis in tenths mode to apply a radial load of 100 pounds at the end of the workpiece. The end of the shaft deflects 2 thou 5/10. Increasing the load to 250 pounds of force, we get a reading of 6 thou 3/10. Here is a summary of these results. For the next test, everything's the same, except this time we're going to use a tailstock force of 400 psi. At the 100 pound radial load, we get 2 thou 5/10 again. And at the 250 pound radial load, we get 6 thou, which is only a few tenths different. Let's take a look at these results side by side and compare. As you can see, there's no difference for the 100 pound load and just a slight difference at 250 pounds. Okay, that takes care of our static test, and the results are clear. Tailstock pressure had little effect on part deflection. But do these findings hold up once we've applied real-life cutting force? Let's find out. We'll be cutting this 2 1/4 inch diameter bar stock. We're going to take 5 pieces of this material and cut them at 200 psi. Then we'll take 5 more pieces of that same material and cut them with a tailstock pressure of 400 psi. And we'll use the same cutting parameters for all 10 cuts. Then we'll line them up and measure them for differences in size and profile. What would be your guess? Which parts would have the best repeatability? The ones cut at 200 psi or the ones clamped at 400 psi tailstock pressure? Let's see. For the 200 psi shafts, we take measurements at both ends of each shaft to get a taper value. Then we compare these 5 values to find how much the taper varies for all 5 shafts. The taper varies by 6/10. Now let's do the same thing for the 400 psi shafts. We find the taper for each shaft and compare these values. The 400 psi shafts vary by 5.5/10. Maybe this seems surprising, but we can clearly see that more tailstock pressure did not make the shaft profiles any more consistent. The large shaft that we just cut had a supported L to D of 8:1. But let's repeat this test on a different shaft to see if this trend holds up. This shorter shaft has a supported L to D of about 10:1. Again, we cut 5 pieces at 200 psi and 5 other pieces at 400 psi using identical cutting parameters. We check diameters and find our taper values. Comparing the taper values, we find the 200 psi shafts vary by only 2/10. And finally, looking at the 400 psi shafts, surprise! The taper variation is 1 thou, 5 times greater than the 200 psi shafts. In this case, setting tailstock pressure to 200 psi gave us more consistent results. Admittedly, this is a small sample of parts, but it supports what we found in testing here at the Haas factory. And we think it demonstrates that 200 psi serves as a good initial tailstock pressure setting. Will 200 psi work for every part every time? Most likely not. But again, it's a good place to start. We hope this section is helpful for the folks who are working with stouter parts. But what about parts that deform easily? To recap, for stout parts, we just recommended a tailstock pressure of 200 psi as a good baseline. But with fragile parts, this doesn't always work. Here we have a 1/4 inch diameter steel shaft and a 49 thou wall 1 inch diameter aluminum tube. How much pressure will it take to deform them? Starting with the parts held at 100 psi, we'll measure runout at the middle of each part as we make 100 psi tailstock pressure increases. Okay, starting at 100 psi, increasing to 200, and then 300, the steel rod deforms significantly by an additional 21 thou. Its neighbor, the aluminum tube, deforms by only 2/10. All the way up to 400 psi, the end of the aluminum tube permanently deforms. Meanwhile, at 400 psi, the steel rod bends so much we don't need an indicator anymore. Okay, so why did we show you this? We want you to realize that 200 psi will probably not work for some weaker parts. The point is, when your part is fragile, take some measurements to find where it starts to deform and keep your tailstock pressure below this point. We've covered a lot. Let's look back for a moment and summarize our recommendations. For most turning jobs, we recommend starting with a tailstock pressure of 200 psi, except at extremes of part size, weight, and cutting load. When your workpiece is very slender or made from weak material, tailstock pressure should be run in the 100 to 200 psi range based on your measurements. And how about really heavy parts? When your part is very heavy, it does make sense to use tailstock pressures between 200 and 400 psi. And when you have cuts that are moving towards the tailstock, it's also a good time to consider running at a tailstock pressure above 200 psi to counter the axial forces that want to pull the part out of the chuck. Okay, so can we run our part already? Yes, but before we do, there's one more thing to consider. The live center. This connects the part to the tailstock. It must rotate freely. It must locate the workpiece precisely and rigidly on center, and it must accept the speeds and loads your machine will exert. Live centers come in many sizes and shapes to fit your tailstock while allowing the best access and support for your parts. In our example, because our part reduces to a relatively small threaded diameter at the tailstock side, we're using what's often called a CNC live center. The reduced diameter shank on this live center allows more room near the end of the part for threading and other finishing tools. If we were using a standard point live center, we'd have to be very careful not to make some contact here. Let's look at the CNC and standard point center side by side. We've already mentioned that the CNC center gives you more clearance, but it is weaker, so it may introduce some chatter. By comparison, the standard point center is more rigid, so you might opt to use it to cure chatter problems. Now, live centers have three main characteristics that you need to keep in mind when setting up your job: maximum RPM, part weight limits, and axial force limits. If you were to max all of these out, your live center would wear down and last a fraction of its normal life. On the other hand, when you run your live center at moderate RPM and weight loads, tailstock force becomes the main factor in live center life. Yet another reason to keep your tailstock pressures low. Live centers do wear out, especially if they are mistreated or abused, so take good care of your investment. Let's check the condition of this used center. First, we're going to check out how smoothly the bearings roll. Rotate the tip 4 revolutions, and then keep rotating in that same direction, feeling for smoothness of rotation. If it's smooth, the bearings are likely in good condition. Next, let's check the runout at the tip. The reading is a little jumpy and it's above this live center's specifications, but it's still acceptable for the parts it's supporting. In contrast, here we have a well-worn center. The tip has significant damage, and when we indicate even the smoother sections, we get jumpy indicator movements. These bearings and the center's tip are damaged. It's time to rebuild or replace this center. Make sure that the tapered side of the live center is clean, rust-free, and has no dings or other damage. Visually inspect the condition and cleanliness of the taper in the tailstock as well. There should be a perfect sliding fit into the tapered tailstock bore. The correct method for removing the live center from the tailstock housing is, of course, to use a steel drift and hammer to break free the taper's tight fit. A badly stuck live center is rare. If it does happen, contact your local HFO service rep. Okay, can we make our part now? You bet. Let's return to the profiled and threaded shaft we looked at the beginning of the video. We'll use a tailstock pressure of 200 psi, since we know this is more than sufficient to keep our part in place without any unnecessary amount of force on our part and machine. With all the aspects of our tailstock support accounted for, we're ready to run our program. But instead of just watching this part run with the tailstock supporting it, we thought it'd be a good idea to watch how it performs running alongside a separate run made without the benefit of tailstock support. Each of these parts are running with speeds and feeds optimized for the amount of support available. Machinists sometimes worry that they'll lose time waiting for the tailstock to clamp their part, but tailstock support usually allows higher speeds and better finishes. The tailstock supported part is able to run considerably faster since it is held in a much more rigid state. As our part reaches completion, we can see that even though the tailstock supported part started cutting after the unsupported part, in the end, it finished well ahead with a lower cycle time. It took 1 minute and 55 seconds to cut the tailstock supported part, and 2 minutes 50 seconds to cut it without a support, a significant difference. And we can also see visually there is significant chatter on the front journal as well as in the threaded section of the unsupported part, whereas the same areas on the tailstock supported part look good. Let's see what the actual difference in finish is between the unsupported and supported parts. To make an accurate comparison, we use a surface finish checking instrument to measure both of the finished journals on each shaft. First, we check the rear journal on the unsupported shaft and find a reading of 59 micro-inches. Moving to the front journal, we find a much rougher finish of 121 micro-inches. This should be expected since this feature is cut hanging out at a 4.5:1 length to diameter ratio. Moving on to the tailstock supported part, the rear journal has a finish of 55 micro-inches, and moving forward to the front journal, we find an equal value of 55 micro-inches. It's easy to see there are great reasons for using tailstock support. Well, that wraps up this tailstock fundamentals video. We hope you found it useful, and thank you for watching.